Hello ma'am. My first question is, what is the Kelvin Planck statement and Clausius statement? Please explain with diagram. Second question, please solve one problem on the Kelvin Planck statement as well as Clausius statement.
Let us first understand the Kelvin Planck statement, which is the second law of thermodynamics, with the help of diagram. It states that it is impossible to construct an engine working on a cyclic process whose sole purpose is to convert heat energy from a single thermal reservoir into equivalent amount of work. Now this statement is about the heat engine. Now what is the purpose of heat engine? It converts heat energy into mechanical work. So the purpose of heat engine is the conversion of heat energy into mechanical work. Now this heat engine is working on a cyclic process. That means heat energy is getting converted into mechanical work, and again mechanical work is getting converted into heat energy. Now the purpose of heat engine is to convert heat energy from a single thermal reservoir. So the heat energy is taken from a thermal reservoir which is at high temperature, and it converts into equivalent amount of work. So according to this statement, we will draw one diagram. So here is the high temperature reservoir at temperature T1, and the heat is taken by this heat engine from this high temperature reservoir. So this heat, we will say Q1, is taken by the heat engine. Now according to this statement, the sole purpose of this heat engine, that means only purpose of the heat engine, is to convert whole amount of heat energy into mechanical work. So we will say that is Q1 is getting converted into W. But if we observe this statement, then it is written that this is impossible. So this whole structure is impossible. Then we will understand what is the possibility hidden behind this statement. So it is impossible to having single thermal reservoir. That means there should be at least two reservoirs. And the purpose of the heat engine is the conversion of the heat energy into mechanical work, and it operates within two reservoirs, that is the high temperature reservoir at temperature T1, which is known as source, and low temperature reservoir at temperature T2, which is known as sink. And here is the heat engine. Now we will take here the heat from the high temperature reservoir. So this heat energy is known as Q1. Now the purpose of heat engine is to convert this Q1 into amount of mechanical work, but some of heat energy is getting rejected to the low temperature reservoir, and we will show that the heat rejected to the low temperature reservoir is Q2. Now the difference in between this Q1 minus Q2 is converted into mechanical work. So we will write here Q1 minus Q2 is equal to W. So this is the work done W, which is output. Then the heat energy Q1, that is the input to the heat engine. Now if we observe this statement, then this is the Kelvin Planck statement, and which is the second law of thermodynamics, and according to second law of thermodynamics, here is the work done, that is Q1 minus Q2. Now the machine or engine which violates the second law of thermodynamics is known as the perpetual motion machine of second kind, and this violates the second law of thermodynamics because this diagram is impossible. So we can say that this is the PMM second, that is the perpetual motion machine of second kind, and for this heat engine which is having 100% efficiency, because the whole amount of heat energy is getting converted into work. But in actual practice, this type of heat engine does not exist. Now we will calculate the efficiency for this heat engine. So here efficiency is nothing but output by input. Output is work obtained and input is Q1. So we will write here Q1 minus Q2 by Q1. So we will simplify this 1 minus Q2 by Q1. Now if we observe this Q1 is equivalent to T1, Q2 is equivalent to T2. So I will write 1 minus T2 by T1. We will solve one problem on Kelvin Planck statement. I will read what is the given question. A reversible engine is supplied with heat from two constant temperature sources at 900 Kelvin and 600 Kelvin and rejects heat to a constant temperature sink at 300 Kelvin. The engine develops work equivalent to 90 kJ per second and rejects heat at a rate of 56 kJ per second. Estimate heat supplied by each source and thermal efficiency of the engine. So this was the given question. We will first draw the diagram as per given data. It is given that the heat energy supplied to the engine from two different higher temperature reservoirs, and the temperature given, that is 900 Kelvin and 600 Kelvin. So we will draw here two higher temperature reservoirs at 900 Kelvin and 600 Kelvin. Heat is supplied to the engine. Now what is the work output? So work output from this engine is given 90 kJ per second, and the heat rejected to the common sink at a temperature of 300 Kelvin, and the amount of heat rejected, that is equal to 56 kJ per second. So as per the given data, we will draw here the diagram to higher temperature reservoir, and now from these two higher temperature reservoir, the heat energy is supplied to the engine. So we will take here the first higher temperature reservoir, that is at temperature T1, and the heat energy supplied is Q1. Now this heat energy supplied is used by the engine, and the remaining heat is rejected to the sink. So the heat rejected to the sink, we will say that is Q2. Then we will move for the second higher temperature reservoir. So here is the Q2 heat rejected at a temperature T2, and T2, that is the temperature of the sink, that is equal to 300 Kelvin. Now here T1 and T2 is getting completed. Now we will move for the next higher temperature reservoir at a temperature T3, that is equal to 600 Kelvin. Now again the heat energy supplied from this higher temperature reservoir, that is Q3, to the engine. Then again some amount of heat is used by the engine for this work, and the remaining amount of heat is rejected to the sink, which is at temperature 300 Kelvin. So the amount of heat that is getting rejected is, we will say, Q4. So this Q4 is rejected to the sink at a temperature T4, that is 300 Kelvin. And what is this total amount of heat rejected? That means we can say that the Q2 plus Q4, that is equal to 56 kJ per second. So I will write here Q2 plus Q4, and that is equal to 56 kJ per second. Now the work is done by this first higher temperature reservoir is known as W1, and here from the second higher temperature reservoir is W2. So we can say that W1 plus W2 is equal to 90 kJ per second. So I will write here W1 plus W2 is equal to 90 kJ per second. Now we will solve the problem. So we have to calculate what is the maximum efficiency. So for a calculation of maximum efficiency for this engine, we have to take the ratio of output by input. So what is the output? That is this total work. So total work is 90 kJ per second, that is given. But what is the input? So input is this heat energy, that is Q1 plus Q3, that we have to find out. So how to find out? So for that we will take the formula for the efficiency for this first higher temperature reservoir, and then we will take the formula for efficiency for the second higher temperature reservoir. So for this first higher temperature reservoir, heat supplied Q1, heat rejected Q2, and work is done, that is known as W1. So how to calculate the efficiency? So we know that efficiency, that is nothing but the output by input. Output is work done and input is heat supplied. So W1 by Q1. So what is the W1? So if we observe this, then W1 is equal to Q1 minus Q2. That is the difference in this heat energy. So Q1 minus Q2 by Q1. So this Q1 is equivalent to T1, Q2 is equivalent to T2. So we will write T1 minus T2 by T2. So we will put the value of T1, then T2 300 and again 300. So 0.67. So we can write here as in eta1 is equal to 0.67. So 0.67 Q1 is equal to W1. So we will write 0.67 Q1 is equal to W1. And what is this W1? So W1 is Q1 minus Q2 and which is equal to Q1 minus Q2. So this is the first equation. Now we will move for the second higher temperature reservoir. So here efficiency in eta 2 is equal to W2 by Q3. So what is this W2? So here is the difference in between this heat energy, that is Q3 minus Q4. So when we put here the value, so Q3 is equivalent to T3, Q4 is equivalent to T4. So T3 minus T4 by T3, that is 600 minus 300 by 300, which is equal to 0.5. So if we put this value 0.5, then we can say that W2 is equal to 0.5 Q3 is equal to W2. And what is this W2? That is nothing but Q3 minus Q4. So here is the equation number 2. Now if we observe the given data, then W1 plus W2 is equal to 90. So we will write here W1 plus W2 is equal to 90. But W1 is equal to 0.67 Q1 and here W2 is 0.5 Q3. So again I will write here 0.67 Q1 plus 0.5 Q3 is equal to 90. Now I will write here, this is the equation number 3. Now again, if we observe the given data, then Q2 plus Q4 is equal to 56. So here this is the equation number 4. Now if we observe here the equation, these two equations are in between Q1, Q3, Q2 and Q4. Now we have to find out what is Q1 and what is Q3. So we have to remove this Q2 and Q4 and we have to take the value in terms of Q1 and Q3. So what is the relation in between Q1 and Q2? So if we observe the equation number 1, then 0.67 Q1 is equal to Q1 minus Q2 and 0.5 Q3 is equal to Q3 minus Q4. Now what is the value of Q2? So we have to remove this Q2. So for that, if I transfer this Q2 to the left hand side and this Q1, that is 0.67 Q1 to the right hand side, then Q2 is equal to 1 minus 0.67 bracket complete Q1. So we can take here Q1 as a common. So 1 minus 0.67, that is 0.33 Q1. So we will write the value of Q2, that is 0.33 Q1. Now in the same way, if we observe, we have to remove this Q4 and we have to write the value in terms of Q3. So Q4 I will shift to the left hand side and this 0.5 Q3 I will shift to the right hand side. Then 1 minus 0.5 bracket complete Q3 is equal to Q4. That is 0.5. Q4 is equal to 0.5 Q3. So this is the equation in terms of Q1 and Q3. So I will write here is the equation number 5. Now we will solve this equation number 3 and 5. Both equations are in terms of the Q1 and Q3. So it is easy for us to calculate the value of Q1 and Q3. So if we solve this equation, now here 0.5, 0.5 as a common term. So if we subtract this equation number 5 from equation number 3, then this 0.5 Q3 is getting cancelled. Then 0.67 minus 0.633 Q1 is equal to 90 minus 56. Then we will get the Q1, that is 100 kilojoule per second and Q3 46 kilojoule per second. Now how to calculate the efficiency? So efficiency, that means output by input. So output is 90, that is W1 plus W2 90 and input is Q1 plus Q3. That is 100 plus 46 and which is equal to 0.616. So in percentage 61.6%. And this is the answer by using Kelvin Planck statement. let us understand the Clausius statement, which is the second law of thermodynamics, with the help of diagram. It states that it is impossible for a self-acting machine working on a cyclic process to transfer heat from a body at lower temperature to the body at higher temperature without the aid of external agency. Now we will construct the diagram according to this statement. Now there is the self-acting machine, and which is working in between two reservoirs, that is the lower temperature reservoir and higher temperature reservoir. So we will construct here the hot body at temperature T1, cold body at temperature T2, and here is the machine. Now what is the purpose of this machine? Is to transfer the heat from a lower temperature to the higher temperature. So by this machine, heat energy is taking out from this cold body T2. So we will say that this heat energy is nothing but Q2, and it is getting transferred to the hot body at temperature T1, that is here is Q1. So there is no any aid of external agency, that is no any extra work done is getting added. So if we observe here, we can say that Q1 is equal to Q2. But according to Clausius statement, this whole structure is impossible. Then what is the possibility hidden behind this statement? So we will again try to understand what is the possibility. So it is impossible, this structure is impossible without the aid of external agency. Now we will add here the external agency, that is the work done. Then this whole structure or whole purpose is possible. Now in actual practice, we know that the heat always transferred from a higher body to the lower body, that is the high temperature body to the low temperature body. But if we add the extra work done, then it is possible to transfer the heat from the cold body to the hot body. Now we will take two types of machines. First one is refrigerator and second one is heat pump. Then how the refrigerator works? So we know that the refrigerator maintains the temperature of a refrigerated space at a temperature lower than the surroundings or lower than the atmosphere. So here, if we compare the temperature of refrigerated space and temperature of atmosphere, then the temperature of atmosphere works as a higher temperature reservoir, or we can say hot body. So we will write here as an atmosphere at temperature T1. And refrigerated space is at the lower temperature reservoir. So we will say that the cold body, that is the refrigerated space at temperature T2. Now according to Clausius statement, this is the possibility when extra work done is getting added. Then here heat is transferred from a cold body, that is Q2, is getting transferred by the refrigerator with the help of this extra work done to the atmosphere at a temperature Q1. So from this diagram we can say that when this Q2 plus WR is getting added, then here is the Q1 that is transferred to the atmosphere. So I will write here Q1 is equal to Q2 plus WR. Now how we can calculate the coefficient of performance? So coefficient of performance of refrigerator, that is COPR, is equal to. Now here coefficient of performance, that is nothing but the output by input. Now what is the output, or where the work is to be done? So output is the how much refrigerated space, that is at what is the heat is getting transferred by this refrigerator from this cold body. So here output is nothing but how much heat energy is getting transferred from the cold body by the refrigerator, that is here is Q2, divided by what is the input. So input is nothing but WR, that is the input given to the refrigerator machine. Now if we observe, we will again simplify this, that is equal to now Q2 by WR, but if we observe WR is equal to Q1 minus Q2. So I will say that Q2 divided by Q1 minus Q2. So again we will simplify this, Q2 by Q1 minus 1. So this Q2 is equivalent to T2. So again we will write T2 by T1 minus 1. So this is the formula to calculate the coefficient of performance of the refrigerator. Now why here coefficient of performance is there? Because the input is work done, and that's why we are not going to calculate here the efficiency, but instead of that, because work done is the input, it is known as the coefficient of performance. Now we will move for the second type of machine, that is the heat pump. So for this heat pump, what is the purpose of the heat pump? It maintains the certain space at a temperature higher than the surrounding or higher than the atmosphere. So if we compare that space that is heated by the heat pump and atmosphere, then that space is having high temperature. So at higher temperature reservoir, we have to write that space to be heated, that is hot body at temperature T1, and we have to take the atmosphere as a lower temperature, that is the cold body T2. So here is the atmosphere and here is the space. So that is the space to be heated. So I will write here is the space, that is heated space, and here is the atmosphere. Now again, according to Clausius statement, we have to take the external agency or external work input. So we will say WP. So heat is getting transferred from a cold body towards hot body. So heat energy transferred from cold body, that is Q2 at temperature T2, and it is transferred here, that is Q1. Now if we observe this structure, then we can say that Q1 is equal to WP plus Q2. So I will write here Q1 is equal to WP plus Q2. Now I will write the formula for COPP, that is the coefficient of performance of the heat pump. So how we can write? Now here the temperature of the space is to be maintained at higher temperature. So this here is the work area, or we can measure the how much heat is getting transferred, that is Q1, to this hot body, that is the work done by the pump. So we have to take here the Q1, that is the actual work is to be done on this space, certain space to be heated, divided by input. So what is the input? Input is WP. So Q1 by WP. So again we will simplify this. Q1 divided by WP is nothing but Q1 minus Q2. So again we will solve this 1 minus Q1 by Q2. So 1 minus T1 by T2. So this is the formula that we can use to calculate the coefficient of performance of the heat pump. Now we will solve one problem on Clausius statement. I will read what is the given question. A domestic food freezer maintains a temperature of minus 15 degrees Celsius. The ambient temperature is 30 degrees Celsius. The heat leaks into freezer at 1.75 kilojoule per second. What is the minimum power necessary to pump this heat out? So this was the given question. Let us first draw the diagram as per given data. Now the refrigerator space is given at minus 15 degrees Celsius and the atmosphere or ambient temperature is 30 degrees Celsius. So we will draw here, that is, we know that the purpose of refrigerator is to take the heat from the refrigerator space and reject it to the atmosphere. So if we compare this space to be refrigerator and atmosphere, then atmosphere is at higher temperature level. That means higher temperature reservoir is atmosphere and lower temperature reservoir is the refrigerated space. So cold body or refrigerator space is at minus 15 degrees Celsius at temperature T2. Higher temperature reservoir is atmosphere 30 degrees Celsius at temperature T1. And here is the refrigerator which is having work input as a WR. Now we know that the heat taken from this cold body at temperature T2, that is Q2, and Q2 is given, that is the heat leaks, that is equal to 1.75 kilojoule per second. So this heat is getting leaked, that is Q2, from this cold body, and what is the value of Q1? That is the heat is rejected to the atmosphere or the higher temperature body. So if we observe this diagram, external work is getting added. Here is the Q2, that is the heat is transferred from this cold body. So WR plus Q2, that is equal to Q1. So Q1 is equal to Q2 plus WR. Now we have to find out what is this work input to the refrigerator to maintain the temperature at minus 15 degrees Celsius. So we will first take here as a temperature T1, we will convert this into Kelvin, that is 30 plus 270, 303 Kelvin. Temperature T2 minus 15 plus 273, 258 Kelvin. Now how to calculate the coefficient of performance of this refrigerator? So coefficient of performance, that is output by input, and output, that is the here what is the amount of heat transferred for the space to be refrigerated divided by input. Input is the work done. So here we have to take COPR, that is equal to amount of heat transferred from the cold body, that is Q2, divided by WR. But here WR is unknown. So we have to write this in terms of Q1 and Q2. So from this statement we can write WR is equal to Q1 minus Q2. So our formula is Q2 divided by Q1 minus Q2. But if we observe here, Q1 is unknown. Now if we observe this diagram, Q1 is equivalent to T1, Q2 is equivalent to T2. So we will write this formula in terms of T1 and T2, that is T2 divided by T1 minus T2. Now we can put the value of T1 and T2, and which is equal to 5.73. Now we have to find out the WR. So for that again we will move for this formula. So COPR, that is Q2 by WR. So COPR is 5.73. Then what is this Q2? Q2 is given 1.75 kilojoule per second. So WR is equal to, so if we put the value, then WR is equal to 1.75 divided by 5.73. So 0.305. And what is the unit? So unit remains same, that is this Q2, kilojoule per second. So we can also write 0.305 kilowatt.